last time we say quantum computing is important, is powerful because of what? You use superposition. One of them is superposition, right? That you can achieve the quantum parallelism, right? If you 300 qubits, you get 2 to the power 300 compressed number in that state, yes.
Your discrete layers or discrete levels can be state basis states because you said it's linearly between the two. Is that discrete some way?
Yeah, that's a good question. He's talking about whether quantum computing is discrete or analog, right? So the basis state is discrete in the case we are studying. Okay, so the basis can be, they are all formed by like what you had in classical computer. If you have 3 qubit, 0, 0, 0, 0, 0, 1, 0, 1, 0, right? Like this, right? For example, if n equals to 3, you have 0. Oh, why this is not 3, right? I don't know why I say this is 3. N equals to 3, you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, I mean 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? So these are all discrete. So the basis state is discrete. But so as I said, we can make them into brackets. So I hope you are familiar with this. The first one is not 1, it's just a bracket notation, right? But a general state, it becomes analog because it can be any A0 of 0, 0, 0 plus A1 of 0, 0, 1 plus A2 of 0, 0, 1, 0 all the way to plus A7 of 1, 1, 1, 1, right? So this is continuous. So A can take any value. It's not discrete. It can even take the compressed number. Okay, now, so the basis state is discrete, but the overall state, it can be analog. So it's more like an analog computing. I don't know if I answered your question, but think about this, right? Yeah. Oh, it's just like if you have if you can store one number, if that number, if you allow it to be any value, it is still a finite number. You only have one number, but it can go from any value 0 to infinity, negative infinity. Make sense? Yeah. So like here, I can store 8 numbers, but these 8 numbers are not discrete number itself. It can be 0.11, 0.12345 instead of 0 or 1. Okay, that's a great question. Yeah, makes sense? Okay, so great, we know superposition. Vaguely, we will learn more. Now, but then we say measurement, right? For any states, last time we have an analogy. You are spinning coins on the table. It's spinning, is it head or tail? We don't know, right? We need to do measurement. I stop it. I will get either head or tail, right? Same analogy, just analogy, but now for quantum computing, this is real. A state psi here, is a superposition of 0 and 1. What are the bases here, by the way? Basis state. 0 and 1. How many qubits do we have? 1 qubit. Very good. 1 qubit give you 2 bases, 0 or 1. Spin up or spin down. Spin left or spin right. Head or tail. Okay? But this is alpha and beta continuous. Can be 1 over square root 2, 0 plus 1 over square root 2, 1. This 1 over square root 2 is not discrete, right? Now, if I do a measurement, it's going to be collapsed to the basis state, either 0 or either 1. Okay? Collapse, yes. I just call it a general state, the state or vector of the system, the psi. Oh, definitely, yes, yes. Why is that so? Now, what we in this class we even don't try to think about wave function because you have two formats for the quantum computer mechanics. One is the Schrödinger differential equation form, another is the matrix form given by Heisenberg. That is what we're doing for the matrix form. So they are equivalent. So why wave function is called wave function? You learn something like this in your quantum mechanics, or you saw people talk about this infinite potential well, and then they give you something like, oh, the electron have a function like this. This is the wave function, like a wave, right? This is x, right? This is the space, okay? Now, then you have something like f of x equals to, I don't know, let me just sine or cosine x, whatever. This is not exactly correct, but this is a wave, right? A function, right? But this is also a state. This state can be written as 0. The ground state, right? Very simple. This is the basic element. It's just like I say, what is the components of hydrogen, of water? You say H2O. Okay, you have something called O. What is O? Oxygen. What is oxygen? Well, maybe this is just analogy. You will say, oh, this is oxygen have 8 electron, 8 molecule inside. It has this whole system. But actually, from chemistry, don't care of that. Only care about it has 8 electrons. I don't care about those proton and nucleus. You basically just say, okay, like this is oxygen, like this. Okay, so the state, you can do some projection to the real space, then you can find out the wave function. We won't talk about this. This is quantum mechanics. They are equivalent to each other. So we use this matrix mechanics. It makes our life much easier. We don't need to go through all those difficult differential equations. And we only have 2 states, and it is much easier. Okay, so very good. So this is, you can call this wave function. My pen has some problem. I need to buy a new one. Or the state, and after all, it's just the vector. So very good, right? So that is what I need you to know. It is a state. Okay, I'm so complicated. I only have 1 state also. If I talk about all of us in this classroom, including this building, we can just describe by 1 state. The state at today, this time, that is the state that we have, but it's just too complicated. Okay, good question, right? So we say that when you measure it, you will get into either 0 or 1. 0 or 1 again is a state, a basis state. Okay, the fundamental one. Right? The probability depends on what? It depends on the coefficient magnitude square. Right? For example, if I have psi equal to 0 times 0 plus 1 times 1, okay, like this. Yeah, anyway. Okay. For example, if my psi is actually 0 times 0 plus 1 times 1, which is just equal to 1, right? If I measure it, what will you get? 1. It's always 1 because I will have a chance to get 0. You're right. But the probability is only 0 squared because you're in the basis state. Okay, yeah.
So this is where it gets interesting. Single shot to get 1 plus 1 equals 2. Whereas in quantum computers, it seems like anything you do is probabilistic, meaning you have to do it over many iterations. Or is there such a thing as a single shot measurement of a quantum algorithm or system?
Right, I don't know what you mean by 1 plus 1 plus 1 is an operation, not measurement, right? But let's just go to you talk about the measurement. Yes. For example, if I do psi, I have a state psi equal to alpha 0 plus beta 1, right? How do you get alpha and beta? You either come up with some very smart algorithm that can reflect the value of alpha and beta at the end, or you need to do measurement. But you do one time, you only get one of them. You don't know whether it's You even don't know whether there is 0 or 1, right? You get 0, you don't know if there's a 1 there. So you need to prepare the same sample for many times, and you keep measuring. Then you get the statistic, but you only get alpha square. You even don't know this alpha square. For example, you get 1/2 alpha square. Then the alpha can be, for example, right? Let's say you get 50% chance, which is 1/2. It only implies that alpha square equals to 1/2. Alpha can be 1/√2, can be plus or minus 1/√2, or it can be even plus minus 1/√2i. You just don't know what it is. You cannot get the full picture by measurement. Although there's something called quantum tomography, they're more complicated, but by just this type of measurement, you don't get it. That is true. You cannot get the full information by measurement. So you need to come up with some smart algorithm to extract the information you want. But again, you cannot get every piece of information.
So
now, that's a good point. Maybe I want to move forward. You will see that later. For example, if I only know that it's either 0 plus 1 or 0 minus 1, I can apply a Hadamard gate and do the measurement. If it is 0 plus 1, I'm going to get 0 after Hadamard gate. If it's 0 minus 1, I'm going to get, maybe I mess up. 0 minus, I will get 1 in the measurement. Okay?
I find comparing logic gates versus quantum gates, it seems to me logic gates don't need probability.
Look,
You do a single shot and you have an answer, whereas if you are building a quantum gate, it's an iterative probabilistic process. You cannot just measure on one single.
good question, but here we confuse one thing. I'm talking about measurement, not quantum gate. Remember last time I said that a quantum gate is just a rotation of vector. It's not measurement. I just operate on it. I have not looked at it yet. Your logic gate, classical logic gate, if you don't look at it, it's also just like that. But however, classical one, you can look at it, it does not change the state. Remember what I said? Now we are doing measurement. I'm not doing operation. I'm not trying to do any operation now. I just want to measure what happened to this qubit. And correct, but here is measurement. I don't know what operation happened before. Right? I only have this wave function here. This is final wave function. This is the answer. How do I read the answer? The only way I can do is by measurement. Right? And when I do measurement, I either get 0 or 1. You are right, meaningless. I don't get anything. And that's why in my operation for my algorithm, I need to operate it such that eventually I can get some useful definitive answer, which we will study later. But that is a very good point, right? But remember to decouple measurement and operation in quantum computing. Any other questions? Good. Now, then we say another important feature is the so-called quantum entanglement, right? I'm not sure why this got shifted completely. Oh, sorry. Also to make this one really low, then there will be no problem next time. Now, if you look at this, I'm showing you a state. This is just a state. How many qubits do I have? Do you know? 2. Very good. Because it has 4 basis states. I'm showing you, and no, because you really see 2 qubits, right? 0, 0, right? You do see 2. Of course, it's 2. But it makes sense here. You see it has 4 basis states. 0, 0, 0, 1, 1, 0, 1, 1. Now, You have not learned tensor product yet. We will learn it later. In some sense, I can do factorization into this because the first qubits refer to the first electron. The second qubits refer to the second electron. Right? It's just like your multiplication. 1 over square root times 1 over square root give me 1 over 2. Right? 0 times 0 becomes 0, 0. 1 times 0 becomes 1, 0 plus 1, 0. 0 times 1 becomes negative 0, 1. 1, 1 becomes 1, 1 times negative 1 becomes negative 1, 1. Do you see that? And you keep the order, right? You don't know exactly what I'm doing. The only message I want to tell you is that this system, like I and you, we form a quantum system, turn out that can be described individually. This just describe me, what I'm doing, and then what he's doing. That is equivalent. Then you completely describe the state of this system. Okay? But however, some states, for example, this is a general state. You cannot do this type of tensor product. I will prove to you later. You can never do that. This is the so-called Bell state. And we say they are entangled. Okay? But the special thing is that, do you see that it only contains the basis state? They are highly correlated. When the first electron is 0, the second electron must be 0. When the first electron is 1, the second electron is also 1. Okay? And we call this entanglement. You use a lot in the algorithm, you will see it, and also in quantum communication. Yes. Exactly. Yeah, exactly. For example, another Bell state will be something like this. Right? They don't have to do the same. I always go in the opposite direction as you. Right? Here is not. When you're 0, the other can be 0, or the other can be 1. No correlation. Okay? Good. What's so special? If I form a 2-electron system on the Earth, I do something to make into entanglement state. I can do it. You will know how to do it later. You will use quantum computer to create a real entanglement state on IBM system. It becomes 2 basis states. This time I did not say 0, 0, 1, 1, right? But it is the same. It's just a name. Happy, happy, sad, sad. When I'm happy, my wife is happy. When I'm sad, my wife is happy. That is entangled state, right? Just a name. Now, I send the other electron to 100 light years away. Means the light is going to travel 100 years to reach there, okay? I do it very carefully, so they are still entangled, okay? It's difficult, theoretically possible. Now, I try to do a measurement. Think about I measure this whole state. This is a whole system. The system has 2 basis states that is non-zero, right? So I told you we do measurement. It will collapse to the basis state. So what are the possible results when I measure this system? Both up or both down. Because that is what we just said about measurement. Measurement always collapses to the basis state. You need to memorize this. If you get lost in the exam, memorize this statement. You only can get this, no matter what. Okay? Now, on the Earth, when I measure, of course, I can only measure my electron. The other electron is 100 light years away. But however, they are the whole system. So my electron will be collapsed to either up or down, right? Because they have equal coefficient, 1 over square root 2, 50%. Well, I really don't know how it will collapse. Let's assume it collapses to up. Okay? It's just probability, yes.
So if you're measuring on Earth, you have to measure 100 light years away at the same time?
No, you don't measure, you only measure your electron. I'm 100 light years away, you are on the Earth. You measure, you can only touch your electron. And what you did is just put in magnetic field, shine the lights to measure the energy difference. They say, oh, my electron collapsed to up. What happened to the other one? Based on this entanglement, my electron will collapse to up also, even I did not measure. Okay? And you will do it instantaneously. Okay? So that's why Einstein said this is the spooky action, distant action. He doesn't believe that. He feels that quantum computing, no, quantum mechanics is incomplete. There might be either wrong or incomplete. There must be some hidden variable. Because how can you have this type of spooky action? But the important thing is this one does not violate the general relativity. You don't transmit information, useful information, faster than the speed of light. Now, try to think about that at home. Can you use this to gain something? If it is faster than the speed of light, maybe you come up with this system, you can do something, violates the causality, right? You will find that you cannot. Now, just like in this example, yeah, you collapse to up, but yourself even don't know what is going to collapse to before the measurement. You are not transmitting any information to me. It's true that now I know that you have this collapse up, but it's not enough to do something useful, right? It's very philosophical, but I'm not good at this. Yeah.
So let's say spin of the electron Earth, spin of the electron 100 light years away, so the same. That's what this, isn't that what this is saying? Whatever you do to the electron on Earth, the same thing happens to the electron on the other side, right?
It will collapse to the same, yeah.
Unless we're not measuring, we're manipulating.
Yeah, but however, you don't know the result. The point is that, let's say if you go up, then it means that I'm going to do something. You want to benefit from me, right? Then you will know faster than other people. But however, I even don't know whether it's going to go up or go down due to the probability. It's stochastic, right? So my thing is like I have an example in the book, right? Like we're doing trading. I go to a very far planet and I find out that I don't know whether I will find the gold mine or not, right? And then I tell you. Now, if I find it, I will tell you. Then you please just maybe sell the gold on the stock market, on the commodity market. If I don't find it, then please buy it because it's going to increase price, right? Yeah, I do find it. We have an entangled pair. I try to measure it, but I don't know it's going to spin up or down. So you don't know what happened to me. I still cannot transmit my information faster than the speed of light to you. Think about that, okay? Question?
Yeah, so for the C plus step one, that's one qubit and each state has two variables.
Oh, this is 2 qubits.
Okay.
I also need to add the bracket here. Sorry for that, I'm not clear. This is the state, 2 qubit state. And this 2 qubit state is a linear superposition of two basis states. Each of these basis states is the basis state of 2 qubits. They are not opposite to each other. Why do you say opposite? So this is one state. Yeah, this is both up.
No.
If you are saying this, right? You want to say something like this? Yes, but then this is just equals to this. Right? X hat plus X hat is still X hat. Of course, you need to normalize the constant. But this is a good point, everyone. When you do measurement, you may see something like this. If a basis state, they are just the same, but you change the probability. Good point, yeah. No, in this case, there's no spooky action. It's both up. It's just like classical information, right? You already, just like I have pair of gloves, red, and then you bring red to over there, and then I did not know the color, I check it, oh, red, then of course I know yours is also red. Yeah, and it's definitive, right? We already know, yeah.
You have, that's the
you check the scale, manipulate, check.
No, I mean, here we don't talk about manipulation. This is just a simple classical thing already. We know both are up. And that's it. There's nothing spooky or strange, right? For example, I would just say, I give you a coin, which only has the head, both sides are head, mine are both sides are head. You bring it to the mass, and that's it. I know that you have a coin that both sides are head. Spin up, spin up. The spooky thing here is that you don't know the result before you measure it. You also know the state, definitely, right? But you don't know what happened after you do the measurement. That's what it calls this spooky action. Okay, very good question. Yes.
One more question.
Yeah.
Does each qubit only have two states, or can they have?
Each qubit only has two states because now there is actually a good question. So we deal with this qubit, right? What is bit? Is binary digit, so it means two states. But nowadays people also try to study three-level system, four-level system. Then it's not called qubit. It's called qubit for three-level, and some call qubit or qquark for the four-level, right? Then you can have multi-level. But now we just use two-level, easier to manipulate usually. It's just like our computer. Our classical one, it can be either 0 and 1. In principle, you can do decimal or 0, 1, 2, 0, 1, 2, 3. Yeah, good question, yeah.
So I guess Reference has been able to do this in the lab, let's say,
Yes. Entanglement, they already done this through the quantum communication. Right? The longest one, I guess, is China. They was able to build a secure communication channel from the Earth to the satellite. And they have successfully done this entanglement. Use photonics. It is there already. But this entanglement is not actually what is so spooky. It just not like spooky. But this one is not a problem. Later, I will tell you when we talk about the Heisenberg uncertainty principle, I will show you why Einstein said that it's incomplete. This one does not affect anything yet. It only affects us who have not studied it before and feel, wow, so cool, it can affect. But actually, there's a more deeper way that make Einstein think that it's wrong. And then people comes up with something called Bell's inequality. And people keep trying to do experiment to prove that looks like quantum mechanics is correct. But that is always not 100% sure. But we'll discuss that later, okay? Greg, you are very curious, but let's just go ahead. Now, we understand the qubits, right? Quantum computing is powerful because of the superposition, and other is entanglement, right? I hope that now you understand what is entanglement discussed so much. Don't get distracted by this spooky action. Right? Remember, entanglement is just that there's some correlation between the 2 qubit, 3 qubit, 4 qubit, in such that you cannot factorize it into subsystem. You always need to describe them as a whole system. If you can decompose into subsystem, it's easy. You can use classical method to solve all the problem. And on the other hand, because you cannot factorize it, entanglement will help us to solve more complex problem. Memorize this for now, okay? So now we know the state is a vector. Then what is a gate? What is really a gate? A gate is nothing but just something to rotate the vector and the states in the corresponding space. That is a gate. Just think about, I have the vector in this space. When I apply a gate to it, it will just rotate. But it's not the space we are living. It's a hyperspace. For example, here I show something called Bloch sphere. I deliberately don't talk it at the beginning. I will discuss almost at the end of this class because it can be confusing. And I don't think it's necessary to discuss now. But it's very tempting to use this to explain some of the phenomena. For example, for this Bloch sphere, on the surface of this sphere, each point represents the state of 1 qubit. This north pole is the state of 0. This south pole is the state of 1, right? That's why, but remember, this is not a vector in the real 3D space. What I say is we embed this hyperspace into a 3D space. What is the dimension of one qubit? Can you tell me? How many basis states it has for one qubit? Again, 2. So what is the dimension? 2D. It's not, it is smaller than your 3D. It's just like the plane. However, it's not a 2D plane because it allows complex coefficient. Your 2D plane, you cannot have a complex coefficient. You have a 3x plus 4y. You cannot have 3x plus 4iy, right? But this sphere, this 2D space, which is not our 2D plane, allow complex coefficient. Okay, so it's more complex than the 2D plane. Yeah. Yes.
End up being a psi, which is now
Very good. I don't want to answer your question because just like what I said, this can make you very confused. That's why I don't want to discuss Bloch sphere at this point. Okay, so ignore it for now. I am going to show you in lecture maybe 20 why that complex number will map to this surface. The hint to you is you look at the degrees of freedom. This Bloch sphere has the degrees of freedom the same as the complex, the 2D one. And it's true thing about what is the dimension of the surface of a sphere. It's 2D. It actually is 2D, right? But not exactly, because here we also ignore the so-called global phase. So we discuss that later, right? But that is a good question. I just want you to know that when sometimes you look at Bloch sphere, you don't understand why. Remember that it's because it's not a 3D space. For example, in a 3D space, this vector, 0, going up and down, you add them together, what will you get? Up vector and down vector. In 3D space, what will you get? 0. That becomes 0 vector, right? But do you see that we have been doing 0 plus 1 with no problem? It doesn't become 0 if alpha equal to beta. That is just because this is not a vector in 3D space. 0 plus 1 becomes plus. Okay, now you don't see that. I'm sure that you don't see that. But now maybe I can tell you 0 plus 1 divided by square root of 2 equal to plus. So I'm thinking this point plus this point equals to this point. Okay, that's why it is confusing. Right? So you know that it's confusing. Don't worry, now we will study later. Now just put the Bloch sphere aside. Okay, but here I try to show you it is rotating. So we have gate. So what is a gate? Gate is not a transistor, not a group of transistor, LAN gate, not gate, right? You learned this in your digital circuit, the gate. Gate is just a laser pulse. I have qubit here, I shoot the laser pulse or shoot the microwave pulse, then it starts to evolve. The state starts to change. Very easy, right? Just like I stand here, my mother slapped me, I cry, right? Someone gave a gift, I laugh, my state changed, that's it. But classical circuit is what? I run into something and they transform me to be stronger, run into another machine, transform me to be something else, right? That is the classical circuit. And that is exactly what we do in quantum computing, except this is still true. So I mean, all the qubits usually don't move, except something called trapped ion. We move them, but we move them not because we try to do computation. You can say we try to go somewhere to do some computation, but just treat it as a stationary for now, okay? Most of the qubit. Any questions? So we will go into detail, but just like you definitely, you know that there is a NOT gate, 1 qubit gate. You apply to 1, it will rotate around the Bloch sphere to the bottom, okay? You have something called control gate. You have 2 qubits. Whether I rotate to the bottom depends on the value of another gate or of another qubit, okay? No need to go into details. But remember, quantum computing is cool because it allows superposition. And we have this gate, NOT gate, and control NOT gate. You can use any classical logic to do it. But you cannot do that with this so-called Hadamard gate. Very important gates in quantum computing. You can memorize now. Start with 0, it goes into a superposition. Right? Can you imagine that your classical register, I have a 0 stored there, and suddenly it becomes 0 plus 1? Yeah, your professor will say either you are wrong or there is noise. But in quantum register, we can have this. And that is why it's so special. Yeah.
So I guess Bloch sphere.
Yeah. You cannot, it's very difficult. I don't see anyone has a good description. But it's enough, pretty useful for a 1 qubit study. Bloch sphere, later I will tell you, we actually ignore the global phase. I will know what is global phase later. And you have multiple qubits, that phase you cannot take it away. So it becomes very difficult to describe. So only with one of this, but this is good enough for many people for us to under the physics of 1 qubit, the coherence time, or other things. How do you rotate, manipulate the qubit? Yeah, okay.
So the fact that the C not gating, that's just you're not connecting them to the Bloch sphere.
It is not, yeah, good point. Bloch sphere is only to illustrate 1 qubit. C0 gate is not illustrated here. Yeah, good. Sorry for this confusion. Very good. Now, just remind you, what is the classical gate, right? This is a LAN gate. If I know the output is 1, can you deduce what the input is? No, right? Because multiple input will give me 1 for LAN gate. So it's not reversible. What's reversible? It means I can go back, okay? Quantum gates must be reversible, okay? This is C0 gate, we'll learn later. But anyway, if you give me 1, the output has 2 bits, however, right, it's 2 qubits. I will know what the input is. Right? Just memorize this, it needs to be reversible because quantum computing uses quantum mechanics, which is physics, which is depends on the Schrödinger equation. It evolved with the so-called Hamiltonian. So it is reversible. If you look at the equation, the time is symmetric in time in that equation. You can put negative time, it should go back to previous state. So that's why it needs to be reversible. Okay. Here I show you again, I have a sign, which is just a state, right? It can be a state of many qubits, 300 qubits or 1 qubit. I don't know what the content is. I go through different quantum gates. Controller gates, NOT gates, Hadamard gates, eventually it becomes something else, which is rotating in the hyperspace. And it's reversible. If I do an inverse of this gate, and all these gates are reversible, I can get the inverse, I will go back to the original state. This is not possible for LAN gate, right? I have 2 input, it becomes 1 output. How do you go back? Except after measurement. That's why I want to say, this is measurement. So we need to compare this gate to this logical operation, right? Measurement is statistical, probabilistic, okay? And here I want to show you again, emphasize again, this is just the drawing. This is the flow of time instead of the space, right? When you draw the classical circuit, that's what you usually do. Input is 1, I go to the NOT gate, and then I go to the LAN gate, and then I go to another NOT gate. And indeed, in your logic layout, you do have the transistor on the left, you have the wire, have another transistor, a pair of transistors, right? That is do the logic layout. But here, no. Your side just there, you have qubit. Like what I said, I stand here. My father slapped me, and someone give me a gift. My state keep evolving. The qubit, apply a laser pulse corresponding to the NOT gate, maybe this length, this energy, and this pulse length, right? And then another gate, I keep evolve. I am in the space. This represents the time. So why this is important? Because if I show you a circuit that need to repeat 1,000 times, you will say, wow, that is really a big circuit. My silicon chip cannot put this big circuit, right? 1 billion times. And I need to duplicate 1 billion times. But here, When I show a circuit that repeats 1 billion times, it's just saying that you stand there, I'm going to shoot the laser pulse 1 billion times at you. That doesn't change the size of the chip, right? I just not gate, control not, then not gate, control not. Just keep changing the qubit. Okay, so I want you to have this mentality. Yeah. Yeah. You lose the information. Yes. Right? You collapse to the basis state, right? My state was alpha 0 plus beta 1. Now you measure, you either get 0 or 1. I cannot go back to alpha, beta, and
So meaning instead of you did U1, then you
no.
just
In general, no. Correct. Right? Commutative means A times B equal to B times A. It is not. Yeah. So how do we implement the qubit, right? We use the mood. I told you that last time. Doesn't have to be the coin. Doesn't have to be tail and head, which is an analogy. Mood is also an analogy. I can say I'm alpha, a little bit happy today, but mostly sad, right? You also hear this from other people. So as I think that if you want to make analogy to quantum mechanics, you need to use emotion. You cannot use physical system because only emotion allows you to have superposition. Okay. In reality, we may use the electron spin. Now you may say, hey, I did not learn electron spin. My God, should I take introduction to quantum mechanics first? No, because the spin itself is just a figure up and down. Take it as an object, it's just a state. Right? No one to ask you to write down the wave function or whatever. This is elementary, the basis. Okay, the basis. I will give more example later. So any spin can be a linear combination of this state, up and down, 10% up, 90% down, for example. It's just the state. We have not measured it yet. We don't know, right? Once we measure, what happened? Either spin up or spin down. Another thing, this one I did not draw it well. I was lazy. It's a waveguide. I'm going to shoot a single photon into here. Single photon, only one photon. Photon is the light, right? Only one. It can go up or down, right? But it's also a wave. So I have 50% the photon can go up or down because they're symmetric. Nothing determines whether it go to up or down. I can measure it anytime. For example, I put a Geiger counter here on top and bottom. Or maybe the up trigger, then I know, oh, the photon got captured by me on path 1. That means the photon collapsed to 1. You see, again, the state is that where I am. That is the state. The physics, you don't need to even know physics. It's just so simple if you think in this way. The state of photon is that it has some percentage or probability in the upper path, some probability in the lower path. Before I look at it, I don't know where it is. Once I measure it, it will be the upper or lower because there's only one photon. I cannot measure at the both place. Okay? And the state is path 1 and path 2, right? So hand waving, but this is very rigorous. That is the foundation for very rigorous computation, the state. I think about this. It's not easy, but you find that turn out to be very easy. This one is very commonly used. This is a superconducting charge qubit. This is the Josephson junction. We won't talk about it. We'll talk about this in the E274 next semester. But again, you don't need to know that. This class is most about algorithm. This is a superconductor, a junction, a metal insulator metal, a superconductor insulator superconductor device. It also has a capacitor, and then it formed this superconducting island. Well, at lower temperature, at a superconductor, you form so-called Cooper pairs. Cooper pairs means that you have, this is the, let me write it down, excess Cooper pairs, which is 2 electrons. Right, very strange. At very low temperature, you can bind 2 electrons together, but they become an entity called Qubit pairs. And they don't have spin because they are half spin add together become integral spin. They become something called boson. Okay, ignore this thing, just the light, like the photon. The point is here that I can inject 1 extra Qubit pair or 0 extra Qubit pair. Basically, the base state is that I have n equal 0 or n equal 1, right? Extra Qubit pair in this island or no extra, that's it. Just like in this room, we have so many people. Someone come in, we have 1 extra student. No one come in, we have 0 extra student. So that is our state. And again, it can be a superposition. We can be in a superposition of 1 extra student or no extra student. Right? Maybe the student take 2 classes at the same time. So sometimes the student go to other classroom, and sometimes they come here. That is the way we implement the qubit. And how do we manipulate this qubit? Yeah, sine, laser pulse, microwave pulse, whatever, to change it. Okay, yeah. You mean this one? Oh, yes, very good. That's the energy level. Yeah, we're just saying that if it's spin down, in this case, it has lower energy. Spin up, it has higher energy. So I did not go into detail. This is the potential barrier. Sorry. This is even more confusing. This one is not a reliable qubit. Yeah, this is just for fun. Okay, all of these are reliable, I mean, at least physical. Okay. So you see that you need to distinguish the level of 2 qubits. You need to distinguish 0 and 1, right? And they are very tiny. And because they are so tiny, let me show you how tiny it is. This is the qubit's energy separation, 0 and 1. It's about 0.02 millielectron volt. Millielectron volt is the energy and electron gain when you travel across 1 volt. Okay? At 300 Kelvin, that is our room temperature. It is 26 millielectron volt. Okay? So you see that how many times? 1, 2, 3, 1,000 times, right? Our room temperature thermal energy is 1,000 times larger than the separation of the energy of the qubit. Now, what is the separation of energy of qubit? It's just like the distance between this floor and the second floor, right? We're on the 3rd floor and then 2nd floor. Okay, let's say that's about 10 meters. But then you say the Earth is vibrating by 1 kilometer. Then can you distinguish whether I'm on the 2nd floor or the 1st floor? If the Earth is keep vibrating by an amplitude of 1 kilometer, and the distance between the 2nd floor and the 3rd floor is 10 meters. No, all the information got destroyed. That's why we need to cool it down to so-called dilution refrigerator about 10 millikelvin, so that the thermal energy is very small. Now, if the Earth is just vibrating by 10 cm or whatever, I still can distinguish whether I'm at the 3rd floor or 2nd floor. Make sense? Yeah.
So I guess if you're going to compare this thermal energy to the energy states or levels in the qubit system, wouldn't those energy states in the system would be very much dependent on the property, the physical property of the system?
Yes.
So with a good figure of merit, I mean, yeah, the KT we can understand, that's
Yeah.
going down with temperature.
Yeah.
But if you look at superconducting technology versus spin technology,
Very good.
they have different.
Yeah, indeed, that's a good point, right? For different technology, like what we talked just about, superconducting electron and photonic, they are very different in terms of the energy. And actually, what I'm saying is more applicable to superconducting and maybe also electron spin. They are all in the similar order of magnitude. Now, for photonics, it is why some people do photonic computing is because they have a potential to work at room temperature. Because you know, photon is very robust. They don't interact with the environment easily. You can do one photon even at room temperature, you won't say, oh, they just disperse or whatever. So indeed, what I'm saying does not apply to photonic, but except that, I forgot, maybe the measurement, the Geiger counter, you need to go to very low temperature, 4 Kelvin or below, to have a good sensitivity. But you are right, for different technology, we might have different level of separation. Here, actually, is more, what I calculated here is for a typical superconducting qubit. Okay, yeah, so good, yeah. Now, so you can lose this due to noise, so we need low temperature. Then we come up with a concept called the coherence time. We will discuss later again. But the point is that if I at a state, I may lose my energy. So if I was at 1, then I may become 0 because I keep losing energy. I interact with the environment. So this is the time it takes to go from 1 to 0 is the T1 time. Okay. Another is look at this superposition. I was at 0 plus 1. If you remember, it is the so-called plus state, but doesn't matter, it's a superposition. Eventually, I don't know whether I'm 0 plus 1 or 0 minus 1 or 0 plus I1 or 0 minus I1 or whatever. The phase, this is the so-called phase. You lose it. This is so-called dephasing time, right? These are all important because it's going to change the result of your algorithm. So you want to compute the computation before the dephasing time. If my dephasing time is 100 microseconds, you better to have the gate time maybe at, I don't know, 100 nanoseconds, so that at least you can do 1,000 computation before you lose the information. Right? So in quantum computing nowadays, one of the important barriers is that how can I have enough computation before the qubit dephase or decoherent? Okay. So this is about the speed of the gates. Right? Later you may say that, well, I have found a technology, easy, right? Cheap. But it turns out you need 1 second to do the computation. Although you might say, even 1 second, I still have exponential speed up. I can crack the password, whatever. But your qubit or dephase, you cannot use it. Yeah. Yes. Qubit energy I'm talking about is this. Maybe when the energy, right, at 0, maybe this is, I just set it 0 MeV. The energy at 1, maybe it is 0.02 MeV. That is what I mean by separation of the energy. So here, what I'm saying is, this is plotting the thermal energy against the temperature. So I'm saying this value corresponds to the qubit energy, which is 0.02 MeV. So here I'm plotting the thermal energy, and I say this point, thermal energy equals to the qubit energy. Make sense? And this point, the thermal energy, there's nothing. Right? This point, the thermal energy is very low. I'm not correspond to any other system. Good question. Okay. Yeah. Yeah.
So I guess which one of these I know the one on the left, the electron spin, I think does require magnetic field.
Correct.
The magnetic field.
I'm not expert, but I don't think we need that for photonic because it has no effect. For superconducting, this is the so-called Cooper pair box. In simple terms, we don't need that also, but there's some version. Actually, you have 2 junctions together. You use magnetic field to tune the junction energy, something called Josephson junction energy. Because you may have fabrication variation and other control variation, you can tune the magnetic field to set it in the right bias point. But except that, you don't need that for the operation. Yeah. But the simplest form, you don't need to involve the magnetic field. Okay. Very good. Almost the end for this introduction, right? And we say we have error, right? How do we fix the error? We are going to learn this later also. You know that if you have a classical communication, right? I want to tell you on the phone, right? Very noisy, very loud. I want to say, tell my mom, I finished this exam, I passed. You say, what do you say? I passed. What do you say? I keep saying, I pass, right? Sometimes the noise may flip it, say, I did not pass. Right? Sometimes she heard I pass. But if I keep repeating, if the noise is not super bad, most of the time she will hear I pass, right? So that's what you do in classical error correction. The simple one, if you want to transmit 0, you just transmit 3 0. And then maybe one of them will flip. Then you look at that. Oh, I have 2 0 and 1 1. I guess it must be 0. Then I do the correction. Done. Right? But we cannot copy a state in quantum mechanics. If I have state which is alpha 0 plus 1 plus beta 1, and I don't know what alpha and 0 are, there's no mechanism for you to copy. You cannot say I copy many states, and then later I see which one is the majority, then I use that one. This is called no cloning theorem. So we cannot use this to help us to do error correction. Okay? What we do is something called syndrome measurement, which is very smart that people came up with this. It's just like I'm sick. I don't know if I am regular flu or COVID. Then I go to the doctor. Let's say they still don't have this swab. They need to take my blood and find out what virus it is, right? So they can directly measure the virus, detect the virus in my blood. But let's say I have a super smart doctor or a supercomputer with very good machine learning. They look at my face, how much I sweat, my temperature, my heartbeat rate, my coughing, and then they will say, oh, you have just a regular flu. This is possible, right? Just analogy. I do not really measure the virus in my body. They look at my syndrome. Same for quantum error correction. This psi is a state that I care about, the information I'm processing. I have some auxiliary bit. They're useless, but they're auxiliary, very important. I do some control NOT gate, you will learn later, and then they have some entanglement. Now let's say I have some error, flip my bit. Because of this entanglement, once my bit got flipped, it's going to affect the auxiliary bit. It's just like once I got flu, I will cough. And if I got COVID, I know maybe I will lose my sense. They just know that I lose my sensation. They will say, you are not flu, you are COVID. They then give me the COVID medicine to help me recover. Same here. If this one got flipped, then you will do something to the auxiliary bit. We only measure the auxiliary bit. Based on the output of an auxiliary bit, we apply a gate to the bit that we want, right? Okay, you are flu, I give you flu medicine, then you recover. Or you're COVID, I give you COVID medicine, you recover. That's how they do the one way to do the error correction. Okay, yeah. Very good. So people say you can have error in a set. They are not decoupled, right? They are the same. So the analogy is not exactly the same now, right? Then you need to come up with more complicated algorithm. You need to take that into account. Indeed, that is a problem. So you just do it so that you are confident enough. So no one can guarantee 100%, but you just do it, push it to be 99.9999% correct, then it will work. Okay? We do not cover quantum correction in this class. But after this class, you're interested, just go to watch the video, right, from MIT or whatever. They are very good video. Okay? So finally, the introduction is this. After you learn this, right, you can forget all of them. I don't mind, because we're going to go into the details in the following classes. But if you can get the concept, you have the will. You see that quantum computing is powerful because it has superposition. 300 qubit give me 2 to the 300 basis states, and one general state of the 300 qubit has 2 to the power 300 coefficient. A lot of information, but now you see that I cannot get the information. No way for me to do it. To get it, I need to do measurement. And how am I going to get all this statistically correct? I need to do more than 2 to the power 300 measurement, because each of them, at least I want to have 1,000 sample on average, right, to get a confidence. And I only get the probability, not even the phase. I only know the square root at the square of A0 is 1 over 2. I don't know whether A0 is 1 over square root 2, plus 1 over square root 2, or minus 1 over square root 2, or plus minus I1 over square root 2, or any other combinations, right? So quantum computing is only suitable for those that classical computer cannot answer. And in order to get the information, we rely on this constructive and destructive interference. So you need to come up with a smart algorithm so that, for example, whether the function is balanced. The balance means that a function, half of the output, it has 2 outputs, right? The number of one type is the same as the number of the other type. For example, let's say the output is either 0 and 1. The number of times you give 0 is the same as the number of times you give 1. Okay, we will look at this later, one example. Find the period of the function. This is in the Shor's algorithm, right? So I won't explain more today. We will go into this, okay? So I will think quantum computer cannot replace classical computer. Indeed it is. You cannot use it to do 1 plus 1. It's a waste of time. 1 plus 1 is much faster to use a classical computer. But it will be a very powerful accelerator for the difficult problem. Optimization problem, factorization problem, all the problems we mentioned in the first slide. Okay, and those are very difficult to do classically. So that finished my first introduction, and then I realized that I forgot to take my cheat sheet.